In, in the previous lecture on linear combination, we discussed how vectors can be represented as linear combination of other vectors in the vector space when the set of vectors are actually linearly dependent. In this lecture, we will take forward the idea of this linear combination and try to establish certain concepts or certain notions which are known as span, basis, and dimension. So we will see three notions into this lecture. One is span, one is basis, and the last one that we will see in this lecture is the dimension. All these three are notions are closely linked to each other. Okay, so the idea of linear combination was basically stating that a vector from a vector space V, where the field is also given, this can be expressed as a linear combination of a set of vectors from the same vector space V, provided that V and the set of vectors that you have chosen, this is a linearly dependent set. Okay, these vectors are linearly dependent. Then only you can express. Now, the next question arises is, if I have been given a set of vectors, given this set of vectors taken from the vector space, is it possible to represent every vector V in the vector space as the linear combination of the given set W? Is it possible to do this? So please note, I'll repeat this. In linear combination, what we saw was, given a vector V in the vector space represented by this calligraphic V defined over a field F, this vector V can be represented as a linear combination of another set of vectors which we represent by Wi, where Wi's are also in the same vector space, provided the vectors V and the set of vectors Wi form a linearly dependent set. This is what the linear combination says. Now, taking forward this idea of linear combination, the question arises, if I am given with a set of vectors from the vector space, can I possibly represent all the vectors in the vector space through linear combination of this one given set of vectors? There may be other set of vectors also, but if I am given with a set of vectors, can I possibly represent all the vectors in this vector space as a linear combination of this set of vectors Wi? Okay. Now, if every vector V from the vector space can be represented as a linear combination of the set of vectors taken from V. This can be a finite set of vectors taken from the vector space V. Then the vector space V is said to be the span of the set Wi. Or in other words, we can also say the set Wi spans the vector space V. Okay, so spanning means what? So essentially, what does this mean? Is if I'm given a set of vectors, I can sweep through the entire vector space and cover all the vectors in the vector space using this finite number of vectors. So how I'm going to cover all the vectors in this vector space? So what it says is, given this vectors, you scale them up by appropriate scaling factors and add them up, you'll get a vector. Now you keep on doing that, you'll be able to generate all the vectors that are there in the vector space. Basically, you cover the entire vector space just by using these vectors with the help of appropriate scalings and addition operation. Okay, so that is what this spanning actually means. Okay, the set of wi's can be used to cover the entire vector space or to represent the entire vector space. Okay, so that is why we say that V, the vector space V, this calligraphic V, is equal to the span of W. This is how it is denoted. For example, let us consider the vector space R2 with a field being real. So this is basically a real vector space. Okay. So we are considering a real vector space. Now consider a set of vectors. Let us denote it as 1 is 1 0 and 1 is 0 1. For any vector V belonging to the vector space, with V being represented as alpha beta, I can write this as a linear combination of the two vectors 1 0 and 0 1, where alpha beta belong to R2. Let us label this as the set x1. Suppose we have another set x2 for the same vector space, right? Which is, let's say, 1 0 and 1 1. Take a vector V belonging to the same vector space, assuming that the vector can be represented as alpha beta. This can possibly be represented as something of this form, where alpha minus beta and beta, both of them, sorry, this is not R2, both of them belong to reals, which is basically our underlying field. Consider another set. So in the first case, V is definitely a span of x1. Here also we get that V is a span of x2. Consider another set x3 which is 1 0 0 1 and 1 1. We have three vectors in this. If we have a vector V which is represented again, let's say, as alpha beta, how can I represent this in terms of three scalars? So I can represent in terms of the three vectors 1 0 0 1 and 1 1. I can possibly write it as alpha minus gamma 1 0 plus beta minus gamma 0 1 plus gamma 1 1, where alpha minus gamma, beta minus gamma and gamma, both all three of them belong to the field reals. Correct. So here also we get that V is a span of the set of vectors represented by x3. Similarly, for a vector space denoted by R2 cross 2 with the field being reals, if the set x1 is consisting of these vectors, then one can show that V is a span of x1. Similarly, if x2 is consisting of these vectors, you can go ahead and show that vector space V is a span of x2. Similarly, for other vector spaces examples that we had seen, you can find out set of vectors that can be used to represent the entire vector space, and hence V being a span of the set. Okay, now notice one thing. In the first set of examples where we were considering R2, the set of vectors forming the set x1 are linearly independent, and so is true for the set of vectors forming the set x2. But if you notice x3, this set is a set of linearly dependent vectors. So please note that even in the second example where we are considering the vector space of 2 cross 2 real matrices, the set x1 is a linearly independent set, but the set x2 is a linearly dependent set. So span, or the notion of span, does not depend on whether the set of vectors that you are using to represent the vector space is a linearly independent set or not. Okay, but there has to be something special about the sets x1 x2 as opposed to set x3 in the first example, and in the second example for set x1 as opposed to set x2. It is what? It is the following, that x1 and x2 both have linearly independent vectors. Okay, x1 has a set of linearly independent vectors that can span the entire vector space. Okay, I'll put it down as, in example 1, x1 is equal to x1 is a linearly independent set, and V, or the vector space V, is equal to the span of x1. So these two indicate that x1 has the minimum number of vectors that is needed to span the vector space V. Okay. Using the field F. Okay. Because for linear combination we take the scalars from the field. x1 has the minimum number of vectors that is needed to span the vector space V over the field F. So this x1 has got a special name associated with it, and in this case the x1 is known as the basis of the vector space V over the field F. Okay. So basis is what? Basis a set of linearly independent vectors from the vector space V such that vector space V is equal to span of these set of vectors. Okay. So in case of R2, you have always been familiar with using these orthonormal vectors, right? And you label them as x and y. And of course, this is the origin, and then any point here basically representing a vector like this with the coordinates a and b. We represent it as a x hat and b y hat, right? Where x hat is essentially the 1 0 vector and y hat is essentially the 0 1 vector, and a and b both of them belong to reals. You can also represent the same vector AB using the 1 0 vector and the 1 1 vector. Let's say this is your AB. This is the vector 1 0 and this is the vector 1 1. So I can write it as A minus B multiplied by 1 0 plus B multiplied by 0 1, where again A and B belong to reals, right? So notice here that this 1 0 and 0 1 for the first case, or 1 0 and this is 1 1 for the second case, are acting like the coordinate axis. what you have always been using is the orthonormal set of coordinate axes, whether it is R2 or R3. What I am trying to say is you need not use only the orthonormal set of coordinate axes. You can use any other coordinate axis as well. So the axis need not be perpendicular to each other. They can be any other axis inclined at any other angle. Okay. So here this 1 0 and 0 1 act as the coordinate axis, about which we say that your a times about x and b times about y. So a times about 1 0 and b times about 0 1, so that you get the vector ab in the vector space. Or we are saying a minus b times about 1 0 and b times about the 1 1 axis, so that you get the vector ab in the vector space, which is R2 in our case. So this brings us to one more point, is or rather does a vector space V have a unique basis? This, in other words, means that can we associate different coordinate frames to the same vector space V in order to represent the vectors in V. Of course, given a field F. And from the above example, the answer is no. No, vector space V does not have a unique basis. Now, for example, in the case of the vector space R2 over the field of real numbers, one basis is given by x1 and the other basis is given by x2, because the argument that we used for x1 holds also for x2. x2 is a set of linearly independent vectors, and it is a set of linearly independent vectors, and additionally the set of vectors span V. The same arguments also hold for x1 as well, right? V is spanned by x1. So x1 and x2, both of them are said to be the basis of V. Okay, there are two different bases. So I can say x1 is a basis of V, x2 is also a basis of V. And note that these sets are not the same sets. Now what can we say about x3? I think x3 was consisting of the vectors 1 0, 0 1 and 1 1. What can we say about this? Is x3 a basis? The answer is no. Why? even though the vector space V is spanned by the set X3, X3 is not a linearly independent set, or the vectors in X3 are not linearly independent. So X3 cannot be termed or qualified as a basis. Okay, so when we consider the vector space of 2 cross 2 real matrices with the field R, the set X1 that we had described, which was basically 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1, this has linearly independent vectors, and also vector space V is equal to the span of X1, which implies X1 is a basis of the vector space V. What about X2? X2 that we had taken was basically X1 union one more vector, which was 1 0 0 1. So here the vector space V is definitely a span of X2, but the set of vectors or the vectors in the set X2 are not linearly independent. So X2 does not qualify as a basis for the vector space. So from this point, I think you would have now observed that basis, or we also actually made a statement somewhere back during this lecture, and basis consists of the basis is a set which contains the minimum number of vectors wi, as that V, or the vector space V, is equal to the span of the set of vectors represented by W. Okay. The cardinality of the basis is the dimension of the vector space V. So dimension is the number of vectors that are needed to form the basis of a vector space V. So I can write this also as dimension of a vector space V over the field F is the number of vectors non-zero vectors. In most of the lectures in this series, I'll be using the word vectors and the non-zero vectors analogous to each other. If I talk of a zero vector, then I'll explicitly label it as a zero vector. The dimension of a vector space V over the field F is the number of non-zero vectors that form a basis of the vector space V. So, in the examples that have been taken upstairs, for the vector space R2 with field reals, dimension of V is 2. Similarly, for the 2 cross 2 real matrices over the field R, dimension is 4. This is an important point that you should note. Dimension of a vector space V over a field F is independent of the chosen basis of V. So dimension of the vector space is unique. Unlike the basis, which is not unique, you can have infinite number of bases for a given vector space over a field. The dimension of a vector space over a field is unique. If the dimension of a vector space is 2, then irrespective of what basis you choose, the dimension will always be 2, which indicates that the basis will have two vectors that can span the entire vector space. Okay, so or the dimension, rather the number associated with this dimension is a number that is associated with this vector space, right? I can loosely speak of it like that. So this dimension essentially tells you the minimum number of vectors that you require to span the entire vector space. That is what the information is that is carried by dimension of a vector space. In the subsequent lecture, we will take up some examples on basis and dimension, and we will also see that for the same set of vectors, if the field changes, is the dimension affected and is the basis also affected. We will stop here. Thank you.